Fix deep pagination in Elasticsearch without slow or unstable result pages. This is the pattern you'll be able to implement by the end, which opens a consistent snapshot and retrieves a stable deep page without slow scans. I'm Professor Pi, teaching search and IR with simple Python. Deep pagination is a real pain when you need consistent, repeatable pages far into your results. You might be building a web UI that lets users flip through thousands of documents, or a data export job that must stream 1,000,000 rows. Using the usual offset style can make Elasticsearch do a lot of work for every jump. That makes pages slow, and it makes results change under your feet when writes occur. Search after with a point in time fixes both problems by scanning ordered results efficiently and holding a stable snapshot while you page. The intuitive idea is simple. Instead of asking Elasticsearch to skip a large number of hits, we ask for the next slice after a known boundary. We remember the last sort values from one page and hand them back to get the next page. To keep everyone looking at the same version of the index, we open a point in time, which pins a consistent view until we close it. This combo is what makes deep pagination fast and stable. We will build a tiny reproducible flow that you can lift into a real pipeline. You will create a client, index a small set of movies, show why, from, and size breaks at depth, then switch to point in time plus search after to page safely. Nothing exotic. Just a clear pattern you can copy into your data export or UI pagination logic. Now we'll make sure Elasticsearch is reachable before we do anything. This snippet establishes a local Elasticsearch connection and verifies it responds. The Elasticsearch constructor builds a client pointed at http://localhost 9200, which is the default development endpoint. The variable IDX names a working index for later steps, keeping state consistent across the tutorial. The client.ping function sends a lightweight request to confirm the cluster is alive without performing any data operations. If ping fails, subsequent indexing and search calls would not work. So this is an essential readiness check. The printed flag confirms connectivity and tells you the client can proceed to create and query data. Next, we will add a few documents so searches return meaningful pages. This code inserts a tiny readable dataset into Elasticsearch and makes it searchable. The list rows holds tuples for ID, title, rating, and year, so it's easy to see what will be stored. Inside the loop, the client.index call writes each movie into the IDX index using a stable ID and a compact document with rating and year fields that we can sort on. The client.indices.refresh ensures the documents are visible to subsequent searches immediately. Finally, client.count confirms how many documents were indexed. The printed count validates that our test set is ready for querying and paging in the next steps. Now, we'll illustrate the familiar but problematic from and size approach. This example expands the dataset, defines a stable sort, and uses from size to fetch a deeper page. Two new documents are added with client.index. Then client.indices.refresh makes them queryable. The variable sortspec specifies a deterministic order, rating descending, then _ID ascending as a tiebreaker. The client.search call requests page 2 at size 2 via from = 2, returning a slice after skipping the first 2 hits. The variable hits holds the page's results, and we print the last ID to show exactly which item ends this page. This illustrates how from size works, but also foreshadows why large offsets become slow and memory heavy. Next, we'll open a point in time to freeze a consistent view for paging. This snippet opens an Elasticsearch point-in-time (PIT) and collects the token needed for search after pagination. The client.open point-in-time call gives a PIT ID, which freezes a consistent view of the index for subsequent searches. Next, client.search fetches the first page using sort spec and the PIT, so results remain stable even if new writes occur. The variable hits holds the ordered results. The variable SA stores the last hit sort values, which Elasticsearch uses as a cursor for the next page. We print the ID portion of that token to show the boundary we will continue from. The printed ID marks the handoff point for stable, efficient, deep paging. Finally, we'll walk the pages using search after and the same point in time. This code continues pagination using Elasticsearch search after against the same point in time for a consistent view. The variables N and SA track how many items were collected, and the current cursor starting from the token produced previously. Inside the loop, client.search requests the next page using size 2, the shared sort spec, the PIT for stability, and search after equals SA to resume from the boundary. The variable H holds the page's hits. If it's empty, there are no more results. Each iteration increments N by the number of returned hits and updates SA to the last hit sort. The printed total confirms how many items were traversed beyond the first page, proving stable, fast, deep pagination. In a real project, this same pattern maps to export jobs, search UI endless scrolls, or bulk migration tasks. Use the point in time to keep results consistent during the whole operation. Use search after to avoid large offsets and heavy rescanning. Together, they let you page through thousands or millions of items without blowing memory or losing determinism. Recap what it is: a combination of point in time and search after that pages by cursor rather than by offset. When to use it: whenever you need deep, repeatable pages or to stream large result sets efficiently. One caveat: you must manage the point-in-time lifetime and close it when done, because it holds resources on the cluster. Next step: scale this test by running the same pattern against a larger index and add simple timing checks to measure how latency behaves as you page deeper. If practical search tips help your work, subscribe and watch the IR videos.